So let's start with number systems and conversion. We're first going to talk about the decimal system that you're all familiar with. Then we're going to talk about the binary system, and we're going to make the direct mapping to the decimal system so that you understand the concepts better. And then we're going to talk about the octal and the hexadecimal system, with an emphasis, of course, on the hexadecimal system. We are all familiar with what is called positional number systems. Each number is represented by a succession of symbols, which we call digits. In the decimal system, we got 10 digits, starting from 0 up until 9. And as you can see in this example over here, the meaning of which the information that is passed to us by each digit that we use is based on its position in the number. Like in this example over here, that number 1 has a weight of 1000, 9 has a weight of 100, 7 has a weight of 10, and 8 has a weight of only 1. Now, I read those weights from left to right because naturally humans read numbers from left to right. Nevertheless, well, maybe I'm wrong on that, because in some cultures they read numbers from right to left probably. But the point here is that in the examples we're going to see next, and in general from now on, you should be treating numbers from right to left based on their weight. You already start to see some pattern. We start from 1, and we go to 10 times 1, then 10 times 10, and then 10 times 100. So again, the familiar decimal system is one traditional example of a positional number system. Now let's see a little bit of a more complicated example. In this example, we call the leftmost number as the most significant digit and the rightmost number as the least significant digit. Obviously, we say that because the biggest weight belongs to the leftmost number, while the smallest weight belongs to, or it's mapped to the rightmost number. Now, in the decimal system, 10 is called the base or the radix. A number, just like this, can be formulated as you see over here. Now, we assume that there are p digits left to the point, in this case p equals 4, and we also assume that there are n digits to the right of the point, in this case n equals 2. So a representation of number d is along these lines over here. You can describe a number as this. Notice that we start counting from right to left, as I said earlier. So we start always from position 0, then position 1, and so forth up until position p minus 1. So obviously if you got p digits and you start counting from 0, then the most significant digit will be at position p minus 1, so that overall you got p digits left to the point. Now, also notice that regarding the fractional part, we start counting from left to right from -1 to position -2 up until position -n. So remember that we got p digits to the left of the point and n digits to the right of the point. So d can be written as this sum over here. What we call the radix is placed here. Now notice that I is an iterator that starts from position -n. Each digit at each ith position is multiplied by r in the power of I. And as you're going to see later on in our examples more meticulously, this is very important. The basis of the numbering system that you're using defines its overall value at each position. Now, let's make that more concrete with this example over here. Let's start from the non-fractional part. And let's start from right to left. You see that 8 is multiplied by 1. This is because it's at position 0, so essentially this means that r in the power of I in this case is 10 in the power of 0. Then you need to add 7 times 10 in the power of 1, because 7 is at position 1. Then 9 times 10 in the power of 2, and then finally 1 times 10 in the power of 3. Now let's see what happens right to the point. On the right side, on the fractional part, we multiply 5 by 0.1. Why is this? Well, if you start going through the negative indexes over here, 5 is at position -1, so it's multiplied by 10 in the power of -1. Then again, 4, which is at position -2, is multiplied by 10 in the power of -2. So overall, as you can see in this example, and if you go through this example again by yourselves, you will realize that a number can be formulated, written as this formula over here. And another thing to bear in mind is that this formula is universal and it doesn't depend on the numbering system. If instead of the decimal you had octal, the only thing you need to change here is the value of r. Now, digital systems handle two states, as we have seen previously. Therefore, the radix of the numbering system that we use is 2. Base 2 means that we only have available two symbols to use, zeros and ones. Those binary digits are otherwise called bits. Then, following exactly the same rationale as we previously shown, a binary number b can be formulated like this, and can be also, and its value can be written as this. Again, you got a summation that starts from position -n for the fractional part up until position -1, and obviously the base this time is 2, and each time the powers are negative for the fractional part. Now when you cross to the non-fractional part, you start by multiplying with 2 in the power of 0, which means that essentially this is where you get the odd or non-odd numbers, depending on this bit over here being 1 or 0. And gradually you get up until position p minus 1, in other words, up until power of 2 in the power of p minus 1. Here's a very small example. Notice that in order to make clear that we are using the binary system, we put this 2 over here as a subscript. You can do, of course, that with every numbering system. We never do that for the decimal system because we take it for granted. Now, this is an example of how you convert a binary number to what you're more familiar with, in other words, a number in the decimal system. Spend some time to take a look at this slide. If you start from the least significant non-fractional part over here gradually to the most significant one, you will see that we always multiply with 2 in the power of position, in this case 2 in the power of 0, 2 in the power of 1, 2 in the power of 2, and so forth. This means, in other words, that we start by multiplying with 1, then with 2, 4, 8, 16, 32, and so forth. Regarding now the fractional part, let's start this time from the least significant bit. Since this is position -2, this means that you multiply the number over here with 2 in the power of -2, which is 0.25, and then you add the other number times 2 in the power of -1. In other words, you multiply by 0.5. And then if you add up everything together, you end up with the decimal representation of this binary number over here, which is 37.25. Now, in order to make clear the difference, we use the subscript over here to denote that this is the format in the decimal system, while this one is in the binary system. Now, a few more examples. Maybe at this point you should pause the video and go through each and every row on this table to realize that there is a pattern. As you can see, we start from 0, 0, 0 if we're using 3 bits, and this is to represent number 0. Then we add 1 over here for the odd number, the first odd number that we see, which is number 1. Notice that for each odd number here, like 1, 3, 5, and 7, you always have the least significant bit being 1. If you think of it, this makes sense based on the previous slide. Now, for non-odd numbers, you see that the least significant bit is always 0, like for 2, like for 0, like for 4, and so forth. Now, if you take the time to notice a pattern, you will always realize also another thing. You see here that with 3 bits, you can have up to number 7. By coincidence, 2 in the power of 3 is 8, which is just one number greater than the highest, the maximum number you can get here. Now, bear that in mind. Now, we saw that with 3 bits, you can symbolize numbers from 0 to 7. What happens if you would like to somehow write down the equivalent of number 8 and number 9? Well, the answer is that you cannot do that unless you add a 4th bit. Now, once you exceed over here 1, 1, 1, you see that you convert everything to 0 and you add 1 at the place of the most significant bit. Then if you increase that by 1, you add a 1 at the end. So you already start to get familiar with how the binary system works with respect to at least counting numbers from 0 up until the maximum number you're interested in. Now let us try to generalize and get the whole picture. If you're having n-bit numbers, what is the maximum number that you can have? We have already seen that with 3 bits, or otherwise called 3-bit strings, you can have up to number 7. With 4-bit strings, you can represent everything up until the number 15 in the decimal system. These are just some small examples over here. Notice how 7 and 15, they are strings composed only of 1s. So you must have already now noticed that there is a pattern here, and if you're given n bits, then with an n-bit string, the maximum number you can represent in the decimal system is equal to 2 in the power of n minus 1. For example, for 4-bit strings, that is 2 in the power of 4 minus 1, or in other words, 16 minus 1, 15. Now, can you try yourselves to find the binary number which is equivalent to 63? Perhaps you should think about what number is 64. Then convert that to a power and try to think how you would represent 63. Now, what about any decimal number? Again, we see this representation over here. This is when you use the summation of all the numbers in order to get the number in the decimal system. This is how you could try to represent a number in the decimal system based on the position of each bit. Again, remember that left to the point, we start counting from position 0 up until to position p minus 1 for the most significant bit. while for the fractional part, we start from position -1 up until to position -n for the least significant bit. Now, having that said, it's about time that we see things a little bit more systematically and try to converge to an algorithmic process that allows us to convert decimal numbers to binary ones. By algorithmic process, I mean a series of steps that will allow you to easily convert any decimal number to a binary one. Let's consider first the case of non-fractional decimal numbers. If this is the decimal number representation, based on what we've previously seen, then this is equivalent to the second math formula over here. As you can see, what we've done is that we've extracted 2, and obviously, if you do that, then you're left with d being equivalent to 2 times everything you had before, only this time, note that all the powers are the same -1, the same as before, -1. So instead of having p in the power of -1, you got p in the power of -2, then you go to p in the power of -3, and so forth, up until you reach b1. Now, this is easy to understand. Now, what we need to understand is why we do it this way. Before we do that, let's call whatever we have in this parenthesis as q0. So the decimal number is nothing more than just 2 times q0 plus b0, where b0 is the least significant bit. The algorithmic process starts by dividing d by 2 and by keeping the remainder. If it equals 0, then the least significant bit will be 0. Otherwise, it will be 1. Now, once you do that, you treat q0 the same way that you previously treated d. It's a form of a recursive process, if you would like to. So, one thing to notice here is that, again, the powers grow smaller by 1. So q0 is 2 times everything that you see over here up until what is now the least significant one, b2, plus b1. Again, if the remainder equals 0, then the bit at position 1 will be 0. Otherwise, it will be 1. And so forth until the division result is 0. Now, I know that that might have been a little bit complicated in theory, so let's try to understand things with a simple example. Assume that you're given number 179 and you want to convert that to the binary system. What you would do is that you would start by dividing by 2. This would give you 89 and a remainder equal to 1. At the end, when we complete this process, this is going to be the least significant bit, otherwise the rightmost bit of the binary number. Then we continue repeating the same step. This time, what was previously q0, we divided, in other words 89, we divided by 2. And that gives us 44 and a remainder of 1. And the process goes on and on. Every time we divide by 2, we keep the remainder up until we reach this point where we divide by 2, we get 1 and a remainder of 0. And finally, the final step, if you try to divide this by 2, you will get 0 as your result. This is the final step. This is your termination clause. And the remainder is 1. Now remember that the first remainder was the least significant bit. This is the most significant bit. In other words, as you can see here, we start in a reverse order to use the bits. 1, 0, 1, 1, 0, 0, 1, 1. Check it out. This is the most significant bit, and this is the least significant bit. And if you go through all the ones and zeros here in reverse order, you will see that this is the binary representation of what we call in the decimal system 179. Two things to bear in mind here. We always keep the remainders and then we use them in reverse order. Now, let's see what happens when we deal with the case of the decimal fraction of a binary number. Well, before I start explaining, we use some sort of the same rationale, only this time everything is reversed. I'm going to say it once based on the rule, and then we're going to explain things with an example. As you can notice here, when it comes to the fractional part, you can do the same trick. You can extract 2, only this time 2 in the power of -1, and multiply it with the rest. This is equivalent, of course, because it's 2 in the power of -1 to dividing by 2. So the reverse process, in order to convert a number from the decimal system to the binary system, unlike what we've seen before, is this time to start multiplying d by 2 every time. Now, the first time you do that, you're going to keep the integral part, and this is going to be the most significant bit. In other words, the bit which you're going to keep in the position -1, which is right after the point. Then you're going to define the previous product as d1. You're going to multiply it by 2, and again you're going to keep the integral part, which could be 0 or 1, and this is the bit at position -2, and so forth. Now, one thing which is special is that this process can keep going up until you end up with no remainder, or up until you hit a repetitive pattern. This is actually a very good point to remind everyone that during your university studies, you should be independent, which means that if you're interested to find out why this happens, why the fractional decimal numbers, when converted to binary, they can be repetitive, and this can go on forever, you can Google it. And I'm sure that there you will find the answer. Now, notice that this can happen also with rational numbers. In other words, not only with numbers which are irrational. It's worth Googling and finding the answer for that. Okay, so let's now try to do an example of a binary conversion and hope that it's going to clarify things. Now, how would you convert a number which is as simple as 0.1 from decimal to binary system? Well, as we said previously, you keep multiplying by 2. The first time we do that, we get 0.2, which gives us an integer part of 0 and a remainder of 0.2. Now, we are going to keep this 0. We're going to take the remainder and we're going to multiply it by 2. This time we get 0.4, which gives us an integral part of 0 and a remainder of 0.4. Again, the focus here is to keep the integral parts every time and take the remainder and multiply it each time by 2. Now, if you keep doing this, when you reach to this step, you're going to get a result of 1.6, which gives you your first one. Now, this means that the remainder is 0.6, which on the next step, multiplied by 2, gives 1, and a remainder of 0.2. That's interesting. It's not the first time that we see a remainder of 0.2. Now, if you go through repeating the steps, you will realize that you will always be going through these steps. In other words, at some point you will always be hitting 0.2, which falls back to what we previously said in the previous slide about the chance of having a repetitive pattern when it comes to the fractional part in binary form. And this is what it is for the case of 0.1. It's 0, 0, 1, 1, 0, 0, 1, 1, and that goes on forever, even though this is not an irrational number. Now, notice some differences. While for the non-fractional part we started from the least significant bit, here we start with the most significant bit. So when I'm saying that the logic is the same but reversed for the non-fractional part, there are two things to bear in mind. One of them is that you multiply by 2 instead of dividing by 2. And instead of keeping the remainder, you're actually keeping the integral part. Not only that, this time you start from the most significant bit and gradually you go towards the least significant bit. That was the most significant one. And here's the general rule. We keep the integral part and we keep it in order. Now, to generalize things when we consider any base of conversion, for the non-fractional decimal part, remember that you always divide by r, you keep the remainder, and every bit that you find is from the least significant bit towards the most significant bit. When it comes to the fractional decimal part, you multiply by r. This time you keep the integer part, and you're gradually going from the most significant bit to the least significant bit. So we've already seen that decimal numbers, by division, they can be converted to binary numbers. Okay, for the non-fractional part, it's not division, it's multiplication, but you get the point. While from binary numbers, you go back to decimal numbers by means of summation. In general, although this sounds pretty straightforward, dealing with binary numbers to document technical data sheets of, let's say, integrated circuits is tedious. This is because bit strings are long. What we usually prefer is to use octal or even better hexadecimal numbers. Hexadecimal numbers are numbers that use as their basis number 16. And this is because they offer a more convenient shorthand representation compared, of course, to the binary number system. Now, before we proceed with the next slide, I would like to make a small comment here. Decimal numbers are important, of course, because you use them in your everyday life. Binary numbers are as much important too, especially nowadays, because they are used, they can be used and processed by digital circuits. And to wrap up, octal and hexadecimal numbers are a shorthand for binary numbers in order to avoid long multi-bit streams. So I would like to go very quickly through the octal number system because this part of the presentation has already become very long. Obviously, since base 8, you use digits from 0 to 7. The summation method is used to convert from octal to decimal, again, just like from any other system to the decimal system. And things are pretty straightforward. Now, what I would like to note at this point is that since the maximum digit is 7, this already indicates that each digit in the octal system is mapped to 3-bit strings. In other words, if you have a bit string, then every 3 bits you can compress that to 1 digit in the octal system. Again, you can see this in this table. And again, here this slide shows us that we follow the same rationale for converting numbers to, this time, the octal system. If you have, for example, number 56, you start dividing by 8, then the remainder that you get here is 0. This is going to be the least significant bit. Then if you divide again what was previously 7 by 0, then you get 0 and a remainder of 7, which is in this case the most significant bit. Now the conversion from the octal system to the binary one is pretty straightforward, the same way that you saw earlier. Now, what is more interesting to focus is the hexadecimal number system. Now, one important difference from the previous numbering systems that we've seen compared to what you're used to is that there are not enough digits, not enough number digits that you're used to. So when you reach to the 10th digit, which is number 9, then we start using symbols from the alphabet: A, B, C, D, E, and F. Obviously, F is the equivalent of number 15. E is number 14, and so forth. Or if you prefer, starting from A is number 10, B is number 11, then you've got 12, 13, 14, and 15. Again, the summation method is used to convert from the hexadecimal to the decimal system. That is very easy. And from there, you can do a division and convert that to binary numbers. Now, one thing to note is that since the maximum number over here, number 15, is equal to 2 in the power of 4 minus 1, or if you prefer, since the base is 16, which is equal to 2 in the power of 4, this means that every hexadecimal digit is equivalent to a 4-bit string. So you compress long bit streams by a factor of 4 by using the hexadecimal system. Here are some small examples. You should be covered by the processes we've shown earlier about how going from the decimal system to the hexadecimal system and vice versa. And to wrap up, here in this table you see all numbers from 0 to 15, from decimal, in binary, then again in octal, and in hexadecimal. Notice that with 3-bit strings you can only represent numbers up until 7. This table is taken from one of the suggested course books. At this point, I remind to you that the textbooks, excuse me, not course books, the textbooks are recommended, but they are not mandatory in the sense that you are fully covered from the slides that we share with you every week. And finally, again from the textbook, you have some conversion examples over here that include binary, octal, and hexadecimal. And they're equivalent conversions to octal, hexadecimal, and decimal, with all possible combinations. And here you got one small example, just like along the lines of what we previously shown in this presentation.